Yeah, that's later. That's later. Okay, here we go. Today, let's see. There's what I'm going to do today and this week is talk about a few of the visible surface algorithms that we have in graphics, and they're actually pretty straightforward. And there's 5 of them. Okay, one you've already seen, which is called the depth buffer, or the Z buffer. There's one called the scan line. There's one that's called Wornock's. There's one that's called Painters. And there's ray tracing. These are the 5 basic algorithms that people use when they do these, graphics. And they all, the depth buffer is going to be there forever. I mean, because it's just memory. Ray tracing is also going to be there forever. It's just computation. Go ahead.
Which are the ones that are not, like, remember there's one paper that said, like, these are not going to be.
Yeah. Basically, these 2 are the ones that are really used today, right? The depth buffer and ray tracing. The others are not used so much, but they go in and out of vogue. Well, I mean, they're used, occasionally they're used for a while, and then they go out of favor for a while, and then all of a sudden something happens and they come back. Right now the scanline algorithm is kind of out of favor. Not many people use it. I'll kind of explain it, and I almost already have. The Wornock's algorithm is currently, we use it all the time as a base for other algorithms, and the thing that brought it back from the dead is parallelism. Okay, once you have a machine that does things in parallel, all of a sudden this algorithm becomes a little bit more fun to play with, a little bit more interesting. Painters came back with games. Okay, and with the mazes and games, Painter's algorithm came back into vogue, and that's the one I'll show you today. And ray tracing, which I'll do in much more detail as we go along, is kind of just geometric optics and physics done backwards. You have all these rays of light. Think of all these rays of light bouncing around, and a few of them hit your eye, right? Well, you do it backwards. You trace things away from your eye and see what you hit out there, and you bounce light off them, etc., and you do kind of everything backwards. And it turns out it's actually not so hard. I've seen a ray tracer written in about 300 lines of code, which actually produces pretty reasonable pictures. So these are what I'll do. These 4 up here all involve scan conversion. Which is, if you remember from that last, it's that bookkeeping algorithm from last time to try to determine all the dots on a polygon. These kind of do scan conversion, and they also do they're also image-based algorithms in general. They work in image space. This doesn't. This is the exception to all the rules. Okay, and we'll get into it as we go along. But the more you do these, the more you end up with these interesting data structures and computer science problems and things like that. And after all, that's why we're here. And so today I'm going to do Painter's algorithm. And this is an algorithm most people say it came up about 1972 or so. People started doing these. And it's really incredibly simple. Has anybody ever seen Bob Ross on public on Saturday mornings where he paints his landscape of the day, right? And what he does is he paints the purple mountains first in the background, and he paints the real mountains, and then he paints the trees in the foreground. He just paints from back to front. He just paints everything from back to front. Things right over the front of other things. And that's what the Painter's algorithm does. It paints all the polygons from back to front. Okay? It paints everything from back to front. So all right. So basically what it assumes, right, to paint everything back to front, you just take each polygon and you take the backmost polygon, you paint it first, right, completely paint it on the screen. I'd use all your shading, whatever, okay, to paint it on the screen. Then you paint the one in front of that. You paint the one in front of that, the next one in front of that, the next one in front of that, etc. Hopefully by painting completely back to front, right, that by the time you get done, those things that have obscured others, you just painted over them, right, as you go along. And so it assumes a back to front order. Back to front ordering of polygons. Now this is the kicker, of course, is that a back to front ordering of polygons is tough to get, right? So what you got to have to do is sort your polygons first. Okay, take all the polygons you have and sort them. That's what they want you to do. And you know, this is cool, but but sorting polygons is kind of not is kind of tough, because if you have a polygon that looks like this and a polygon that looks like this, how am I going to do this? This goes in front. I got it. Like this. Is that in front? There you go. Is that okay? Which one of these is, right, how do you order these two polygons? Right? And the answer is you chop them up, you clip them. Okay? Well, polygons, we can clip them. Right? But what you got to do is you got to get a sort here that works with this clip. And so the whole idea behind a painter's algorithm is that you sort all your polygons back to front. You take all of them, how many of them there are, 1 million of them or whatever, and you sort them from back to front. And there have been actually graphics engines built that do only painter's algorithms, the graphics engines for PCs, that they only do painter's algorithm, and you have to sort all these polygons. So you can't just throw these polygons at it. With a depth buffer algorithm, you just throw polygons at it, you know, at will, and it keeps track of the depths for each pixel. Okay? With this one, it doesn't keep track of the depths anymore, and you've got to figure it out. So let's see. Okay. I can show you how we sort them, right? We use a binary tree sort. Okay? To show you this, how about a list of numbers? Here's a list of numbers. Let's sort these numbers. And you've all seen this algorithm before. And what it does is it places the numbers into a binary tree. So 5 goes into the root of the tree. And then 3, it either goes to the left of 5 or to the right of 5. Goes to the left if it's less than, to the right if it's greater than, or equal to maybe. Okay? So this one, 3 goes to the left and goes in. 9 here goes to the right of 5. 2 goes to the right of 5, goes to the left of 5, right, and to the left of 3. Right? 6 goes to the right of 5 but to the left of 9. Right? 7 goes to the right of 5, to the left of 9, to the right of 6. Is it looking binary yet? 4, aha. Goes to the right, left of 5 and to the right of 3. There you go. Finally, I got something there. And then 1 goes to the left of 5, the left of 3, and the left of 2. Okay? And you get a binary tree that looks kind of like that. Okay? And then how do you sort the numbers? What's the key word?
Left, right. Left, right.
You do an in-order search, right? In-order is the key word. Right? You do an in-order search of the tree, and you get 1, 2, 3, 4, 5, 6, 7, 9 out. Okay? You just do an in-order search of the tree, of this binary tree, it gets you something out. So here's in order. Search of the tree gets you these things out. Okay? Now, this binary tree this thing works well. Okay? The theorists like this one because it has an n log n type of structure, if it kind of is a full binary tree, it has an n log n type of structure. You can see that pretty easily. I mean, there's n numbers, and in each one of the branches going down, there's only log n things here. Okay? So to insert something takes log n, right? To retrace it takes n. That's an n log n search on the average, right? The problem with these guys is that what happens if I tried to sort these numbers, okay, right? You can see the problem with this search, with the sort, is that if I try to sort these numbers, it's like, you know, well, the tree is just a straight line going down one side, right? Okay? And so you get these, you can get, so if I had 150 numbers here that were almost sorted, you can see the tree is going to basically be a straight line going down tree one direction or the other, for example. So this works, this works, theories like this and all, but it works only when things are really kind of unsorted, right? When they're sorted, it doesn't work very well in general. In fact, it looks almost like n squared, right, rather than n log n, which is what you want. Okay? So, I mean, but you know, this is an interesting structure. Now, what we do in the case of polygons, okay, is the following. Suppose I have a bunch of polygons here. And I'll wave my hands and I'll show you an example here. What I'm going to do is I'm going to put the first polygon in the root here. Okay? And then I'm going to say, is this second polygon, is it in front of or behind this one? Okay? Well, how do you determine if a polygon's in front of or behind? Well, what you do is, if you remember, we had a clipping test that said, you know, all polygons are planar. So we can figure out the normal vector and the plane of a polygon. And we can figure out if polygon 2, all of its points were in front of, right, using that clipping test, in front of the plane of polygon 1. Okay, we could use that clipping test. And see, what I'm going to do is I'm going to do the same thing with polygons here. So let me see, maybe the better way here is to do this one. I have no idea what's going to happen here. Here's P1, let's do this one. P1, P2, P3, P4. And here's my camera, right? Right, looking down here at these things. Okay? And again, in image space, I can assume all the lines are straight. Okay? I can assume all the lines are straight. And so let's put P1 in front first. Okay? And what I'm going to do is look at P2, and I'm going to look at the plane of P1. Okay? And I'm going to ask if P2 is, can I renumber these so I can make this discussion easier? Okay? I'm going to ask if P2 is on the inside or the outside, right? In front of or behind. And you can see that if I get the normal vector to P1 here, right, and I point my normal vector toward, I've got two of them I can choose from. I take the one that's pointing at the eye point. And then I say, if all the vertices of P2 are inside, right, on the inside of this plane, I'm going to say then P2 is in front of this one. Otherwise, it's behind. And I can test all the vertices here. And if all the vertices of P2 are on the inside, then it's going to be in front of. If all the vertices of P2 happen to be back here, it's going to be in behind. All right? And I can put P2 maybe here. Right? It's in front of. Right? And in front of goes right, and behind goes left. Now, P3 is kind of interesting because I ask, what's the relationship to P3 to P1? And this is where the algorithm kind of gets interesting, is because you can kind of see here, like that example I've made over there with the V and all, that if I take the plane of P1, all the vertices of P3, this is a 2D picture, but you can envision it in 3D maybe, all the vertices of P3 don't lie either on one side of it or another side of it. Okay? And so what I do is I split P3. I clip P3 against the plane of P1. Okay? Getting two things. So I'm going to call it P3A and P3B. Getting two things. Okay? And I'm going to put P3A over here. Okay, that's behind. P3B is in front, but now I've got to test P3B against P2. Okay, if I take the normal vector to P2 like this, and I test P3B, it's going to be always behind P2. So this one goes over here. See what's happening? As I go down, what I do is I split these things in two pieces, and then one piece goes down the left side of the tree and the other piece starts down the right side of the tree. Okay? And P4 out here, oh my God, okay, P4 splits, right? So I got P4A and P4B. If I split P4 along the plane of P1, P4A goes down the left side of the tree now, but now it has to look at P3A, and it happens to be on the inside, front of P3A, so P4A goes here. And P4B is on the is in front of P1, right? So I now have to look at it in P2, and you see that P2 crosses there. Okay? So I'm going to split it into two other pieces. Oh my God. Can I quit here? Okay? Can I quit here? You can all nod and say, oh yeah, I see the mess you're getting into. Okay? And you can, but when I'm done here, right, what I can do is say, okay, I draw P3A first, right? Do an in-order search of this tree. Draw P3A first, then P4B, P1, right? And keep going. Right? That I can trace this tree back to front and get it back to front ordering. Now these things are usually done on mazes and things where it's great for mazes and things where things look like this. They all kind of nicely match up and you don't have these problems with clipping them in the middle as much. Okay? And they work very well, but moral of the story is if you have a completely polygonal environment, you can get it back to front ordering for these things. Okay, you can get it back to front ordering. And these things are called BSP trees. Okay? Binary state partitioning trees. And at each node, we not only have the polygon, we keep a normal vector at each node, right, for the polygon, so that we can clip and build this big, huge tree up. And it works pretty well, right, to get it back to front ordering. And then we just paint them, right, back to front. We just paint them when we're done. Traverse this tree and you're done. Now, this algorithm was thought to be really cool and all, and it's still cool today because people do use it a lot. And it's got its problems though, because we've already found out over there that if things are almost sorted, okay, that this algorithm, this sort algorithm, doesn't work so well. You get these great big huge unbalanced trees out. All right? And the same thing happens here, because human beings, when they design something, they don't design one little polygon square here and then another little polygon square over the other side of the building over here and then another one back over here and another one over there. I mean, we design things in groups. Okay? And so basically what happens is these groups all get together, right, and you get this kind of a little subtree for the group, right, but it's actually slanted a little bit because we tend to be organized when we do these things. Then there's another group, another group, another group. And what happens is these trees still tend to be pretty skewed, right, and that's the killer for this algorithm, is when you get these skewed trees, because then your algorithm acts like an n-squared algorithm and you're in trouble. So people have all kinds of tricks with these. We quite frequently select the first polygon. We select each polygon randomly from the list of all polygons. We don't select them in order. We select them randomly. And do that to try to balance somewhat the tree, etc. But balancing this tree is a tough task. Okay? Is a tough task. And it's one of the things that's done over and over again. But, it works. The BSP tree algorithms actually work. And it's kind of fun to watch these things draw. The other thing that happens is that things tend to split up a lot into very small pieces. Very small pieces. Okay, some of them less than the width of a, sometimes long, thin pieces less than the width of a single pixel. All right, they tend to split up into very, very small pieces. For example, if you have a polygon over here, and you have one way over here, right, that happens to cross the plane of that one, and it happens to go down the same branch of the tree somehow, this one's going to get split. Even though it really makes no difference, okay, how it's going to be done.
But if you're doing something like that, why don't you just use like a Z buffer, or because you're talking about something, it seems like you're talking about something that will be on the same memory scale as the Z buffer, though.
Yeah, but, well, there are advantages to doing this. I need to finish the statement here, though, because when you have this type of arrangement, what we usually do is we usually put what we call bounding boxes around these objects. Okay, we put a little box around our object, and if the two boxes don't intersect, right, then we know that we can just take them down one side of the tree or the other, and that's quite often a strategy used to balance the tree, too. As long as they don't have, it doesn't matter where your camera goes, okay? The other nice thing, the really nice thing about this, though, is that once you have this tree stored, okay, you can move your camera point around just about anywhere, okay? You've chosen all these particular vectors and everything for a particular camera position, but what happens if I move the camera over here, okay? Or even over here. What happens if I move the camera over here? Well, all I have to do is, as I'm traversing this tree, what I do is I look at the relationship between this vector and the normal. Right? If their dot product is positive, normally would be like this, so the dot product would be negative. Right? But if the dot product is not negative anymore with these things, I know that my camera point is moved way over here, and I can go, instead of doing an in order where you go left, this, right, you go right, this, and then left. Okay, to actually make things work out. So once you have all this stuff stored, you can move your camera position anywhere. And this is where it gets really valuable. Okay, because now I can move my camera position anywhere I want and traverse this tree to get the ordering out. So again, it's done usually with mazes. It's also done in games a lot to localize the drawing of certain regions. So if you have a character in one region and you have two characters that don't intersect running around, they put planes between these characters, okay? So they know how to, they put planes between the characters, and then they can do a BSP algorithm just on the planes, right, oriented things, and figure out how to draw the characters back to front, okay, which may be easier than doing other things. So this is a scanline algorithm is one that, or not scanline, Painter's algorithm, this one is one that's used. It was dead for a long time, but it's come back because of the games industry. In the games industry, you try, let's see, when we worked with EA, they guaranteed us that any algorithm we did, they could do 1,000 times faster. Okay? And they could, right? Now what they did was they simplified it down so much, right, that, it was so simple that, well, okay, there was the shadows were on the ground were little spheres. And, they basically simplified it down so much. But they could. That's the way they think, is they can make it 1,000 times faster. Well, see, I have time. Let me do Wornock's. Okay, I'll show you one that's slightly different. And Wornock's algorithm looks like this. Here's your window. Okay, and you have a bunch of stuff in the window. All right, you have a bunch of things in the window, and I'll number them 1 and 2 and 3. 3 is closest to me, 1's farthest behind, I guess. Okay. And Wornock's algorithm was kind of clever in that it says it's a classic divide and conquer algorithm. Divide and conquer says, if I don't know how to draw this picture in this window, split it up. Split up the problem into 4 sub-windows. Like that. And then ask the problem of each one of these. Okay? Ask the same question of each one of these. Right? Until it's, so you ask the question, is it easy enough to draw in this window? If so, draw it. Right? If it's not easy enough to draw, split it up into 4 pieces. Okay, and then draw it. So, and when we split it up into 4 pieces, you can see here what we'll do is for each one of our windows, we'll keep a list of the polygons that actually intersect that window. Okay, so that when I split this up into 4 pieces, I only have 1 and 3 now in here, right? And 2 is only in this one. So my lists actually sort of get smaller. You can assume they're going to get smaller as you go along. And, you know, you continually ask this question, and you continually split, okay? Like this. You continually split up windows, okay, until something happens. Well, the something that happens is that it's easy enough to draw. You know, if I split this thing up like this, you can see that these 3 are easy enough to draw now. They don't have anything in them, okay? This one's easy to draw. It's got only 1 thing in it. Okay, and I can just, and by the way, I can clip each one of these things. It's actually not too hard to do. These planes are all nice and perpendicular. I can clip them, right, if I like. But there's only 1 thing in this window and this window, so it's easy enough to draw. All the other ones have 2 in it, and actually that's what we're going to say is something's easy enough to draw if it has nothing in it, or if it has only 1 thing in it. Okay, otherwise it's too complex. You say, wow, that's pretty restrictive, okay? But it's not that bad. And I'm doing, by the way, I'm doing Wornock's original algorithm here. This is not the way we do it today. But, you know, in general, it's not that bad. Well, if you look at this spot in here, there's a big mess in here. Okay, and even if I split it down a few more times, I mean, you know, there's lots of stuff in here, okay? And you know, what's going to happen in here? Well, there's a point at which, have I gotten there yet? No, I haven't. Geez, let's do this one more time, right there, and let's look at this guy. Okay, let's look at that guy right there. Now, polygon 3 for this guy, which is the closest one, right? Polygon 3 is what we call, for this guy, is what we call a surrounder. It completely surrounds this little window, right? Okay? Which means that polygon 3 obscures everything behind it, right? So what I'm going to do is, for those things that are surrounders, and I can figure out if they're surrounders by, if I clip it to the window, and it actually comes out to be the window itself, it's a surrounder. So these surrounders are important because what I can do is I can throw out everything that's behind them. Okay? I can throw out everything that's behind them. So all of a sudden here, 3 is a surrounder for this, so I can throw out 1 and 2, no matter what they do. And now my thing has only 1 thing in it, right? Which is 3, and I can draw it. So this concept of surrounders is very important. Right? Then I get a window that surrounds something, I can throw out everything that's behind it. Okay? So, what do you do? Well, off you go. Split, 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 split. It's recursion, right, folks? Okay? I mean, you can do this a really nice recursive algorithm. Every time you split, you have to sort all your polygons into the windows that they intersect. Okay? And then do the same thing for each window, sub-window. And you're off. Well, now, after 10 subdivisions, okay, 2 to the 10th is 1024, right? So if your window is like 1,000 by 1,000, after 10 subdivisions, you're at a pixel, okay? You're at 1 dot, and you're less than the size of 1 dot. And in that case, we say, take all the things that intersect this dot, right? Pick the closest one. Okay, that tends to be what they say. Take all the things that intersect this dot, just pick the closest one. We'll take that one. Okay, and so Wornock's algorithm is kind of cool. It's fun to watch it work. Okay, and by the way, John Wornock was the guy that invented PostScript, PDF, CEO of Adobe. He's a fairly important guy. But this algorithm it's fun to watch it work, and it works pretty well. It's not too hard to code up because it's all recursion. Again, there's only two things that you have to ask. Number one, is there only 1 thing or 0 things in this window? If that's the case, I just draw it. Number 2 is something a surrounder, right? If it's a surrounder, how do I throw away all the things behind it? Okay? How do I throw away all the things behind it? And, so it's actually pretty easy to write up. We never use this algorithm anymore, though, right? But what we do is we use the fundamental first part of the algorithm that says split the window into 4 pieces and to push and generate 4 separate lists of polygons that intersect these 4 pieces, right? And then split those up and split those up. And why do we do that? Well, we do that because we can deal the 4 pieces off to other processors, okay, in a parallel environment. And we can split the picture up however we want, and we can just deal things off as we go. And typically what would happen was, it was great when you have a very distributed network like the CSIF downstairs, right? We used to take all those machines in the CSIF, and if if you didn't touch your machine for like 2 minutes or so, right, it would send a message back to our dealer, right, that said, "Ooh, this machine's available," and we'd send a little portion of a picture to that machine. Okay, and we started doing this, and we ended up with we could generate some really, really high quality graphics and animations, because at one point we got over 500,000 hours of computer time down there. Okay, just by doing it. It turns out the students don't touch the machines very often. And in fact, we got in trouble because we used a lot of the faculty machines also. Okay, and we found out exactly how often the faculty touched their machines. And so that wasn't that caused us some problems. But anyway, this 1 to 4 split's called a quad tree. Okay. It's called a quad tree, and it's everywhere in our field, these quad trees. Okay? If you think about a Bezier patch, we had an algorithm to split the Bezier patch into 4 pieces. Okay? That was a quad tree algorithm, again. Quad trees are all over the place. There's an extension to this that we actually use, of Wornock's algorithm that we actually use, which takes a cube like this, right, and splits it up that way into 8 pieces. Okay? Splits a cube up into 8 pieces. And then we draw things in this cube like Wornock did, but we also draw them back to front this way. Okay? And there's all kinds of, if you have a surrounder of one of these pieces, then you can forget about all those pieces behind it, etc. These are called Octree algorithms. Right? Octree algorithms. Octree does not have 2 T's, it only has 1 T. But these algorithms are all over the place in our field, and they're very, very useful. Now you can think of Wornock's algorithm here as actually both of these died. Painters came up, it died, nobody used it, and then all of a sudden the games people brought it back out for some specialized game engines, and then it stuck around, especially in the maze games, or the games where you're going through a building or whatever. It's really easy to segment these things up into these things. The Octree algorithm, the Wornock algorithm, again, came up, kind of died almost immediately. It was really kind of an elegant divide and conquer solution, which we all look for in computer science. But then all of a sudden, distributed parallel processing came back up, and everybody rediscovered Wornock's algorithm again, and we've been using that a lot. And so there are variations on these things going through. So I have the scanline algorithm to do yet. I'm going to finish early today. The scanline algorithm to do yet, and then I'll do some on ray tracing. And ray tracing is something, there is a thing out there called POVRAY, P-O-V-R-A-Y. You can go out and get it. You can ray trace things today. If you like, download it to your machine, compile it, ray trace things today. All you have to do is give it a few spheres or something like that, and it's really easy to do. But I'll show you ray tracing, and then the scanline algorithm will do it too. Scanline algorithm came up, died, came back up in about the late 80s, and died again about early 2000. Nobody uses it anymore. And we keep it running around because for some reason, people think it's going to be done. It's going to be used again. So, what I want you to get out of this lecture, there's 5 classes of these algorithms. One of the most famous papers in the field said, This one and this one were dead, right? Never going to happen. Right? One of the most famous papers in the field, written in 1976. And they were exactly wrong, right? Because this one was based on memory. Right? In 1976, you couldn't see the explosion we were going to get in memory. This was based on computer time. Not so much memory, but it just takes cycles and cycles and cycles. Well, no one could see the parallel processors that we're going to have, okay? And in those days, even though they were thought to be the visionaries in the field, right? They were concentrating on these. These have all basically died, come back for special purpose, died, come back again, etc. And some of them will hang around. Wornocks will hang around because it's so great to just take pieces of your image and deal it out, right, to various processors and to let them go. We used to do this all the time when we had big SGI equipment that had shared memory parallelism. Right? You didn't even have to deal the polygons out. Everybody could just access the same, every machine could just access the same part of memory. And it was done all the time with those machines. But in any case, there's 5 of them. They're all very important. If you work in this field very long, you run across all 5 again, over and over again. And one of my students right now is actually coding up a piece of a scanline algorithm to work in something he was doing. There are also things that go in between. There's something called the scanline z-buffer algorithm, right? And that's something that works that people use. And so there's if you kind of plot these out on a board, there's midpoints between them that people sometimes use. And I should mention one more thing about this one. The other thing people like about Wornock's algorithm is that we don't have to stop splitting just because we've gotten less than 1 pixel. We can go much less than 1 pixel, right, and then average the things that we get over this 1 pixel, right, and get rid of our aliasing problems this way. And Wornock's is really the only algorithm that does that well, okay, without a lot of work. You can just say, okay, just double the resolution of the image, right? 1 Wornock's on it, and then average every 4 pixels down to 1, and you actually get things done. You can do it 4x4, 16x16, whatever. Okay. So, all right, I'm done for today, and I will see you on Wednesday. I go over and measure the building.